Okay, transforms are a little bit weird, right? Okay, why? Like, I mean, you see the word transform and it always used to freak me out a little bit. Yeah, what's the point of a transform? Just like in general, to make calculations easier. That's exactly right. It helps you to make calculations easier. That's a big part of it. It also just allows you to see a signal in a different way. Intuitively, you can think about it as like I'm rotating the signal to see it in a different way. Okay, when my 3-year-old builds a puzzle, right, and the puzzle piece is there on the floor, what does he do? He picks it up. First thing is he turns it the right way around to actually see the picture because the back of the puzzle doesn't make sense. And then he rotates it and then he puts it in place. And that's exactly that is one type of transform. He rotated the signal. He took not the inverse, but he took the reflection and then rotated the signal, and that was a transform that he used to solve a very particular problem. When you zoom in on your phone to see a picture better, that's a transform, right? When you rotate a picture on your phone, that's a transform. And all you're doing is you're still looking at the same thing, but you're looking at it from a different perspective. And the Fourier transform is one of these transforms that we as electrical and electronic engineers love because it allows us to see very complicated stuff in kind of a nice, easy way. And hinting at what you said, it also makes it very nice for us to manipulate signals. So that although the Fourier transform has this kind of crazy integral in it, it actually allows us to very easily add a sine wave to a sine wave, convolve it with something else, multiply it, scale it, stretch it out, and all of those things we can very quickly, graphically, actually figure out. Okay, so the Fourier transform is awesome. The Fourier transform is also a pain, okay, because it looks like this. So you have some time signal here, okay, and you plug it into this definition, and really what it's telling you is it tells me how much of a rotating phasor at a specific frequency I need to reconstruct that signal. Okay, so let me just unpack that a little bit. And for that, we actually need the inverse Fourier transform as well. We call this thing h of f, and that's just our Fourier transform. The inverse of this, to get back to ht, we take the inverse Fourier transform of h of f, and that is equal to minus infinity, infinity, h of f times e to the j 2 pi ft, and then df. Okay, so let's just look at the inverse for a second. Okay, what this thing tells us is we've got integration, which I normally just think of as an addition. We're going to add stuff up. Okay, and what we're going to do is we're going to add up a whole bunch of these exponential things. Okay, what's that exponential thing? It's some of us call it a phasor. It's this rotating thing that goes zwank, 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 zwank. Okay, and we're going to add up. It's integration, so we're going to add up a lot of them, like many, many of them. We're going to add up a lot of them. That's what the integration says. And each of them will operate at a different frequency. Okay, there's actually so many of them. It's like a continuous frequency axis. What does this do? H of f, capital H of f. Capital H of f tells me how much should I weigh the rotating phasor rotating at that particular frequency. Okay, I'll explain it again in a second. So this weighs all of these little rotating things. It tells me how much of the thing rotating at that particular f do I need in order to get my signal back. Okay, and that's actually all it is. So if we look at this little picture here, it's a made-up cartoon picture. But if this is our signal and we take the Fourier transform and we get out this little signal here, like this is the magnitude and this is the phase, what this tells me is I actually need quite a lot of the phasor rotating at this frequency because there's a high value. I need a lot less of the phasor, the rotation. I need a lot less rotations than what happens at that frequency. Okay, and that's all that the Fourier transform tells us. Now this property really helps us because it helps us to quickly look at signals and figure out what is happening, where are they pulsing or rotating. Okay, and it allows us to do many other things. Just not, you're just adding up a bunch of rotating stuff, many rotating stuff, and you're weighing them with different weights at the different points where they're rotating. Okay, that's the Fourier transform. Could we have used something else other than the complex exponential for the Fourier transform? Why did we not use like a cosine, which doesn't have imaginary parts and makes me like I can draw it without trying to draw a squiggly on the board? Why did we not use cosine? That's exactly right. Okay, so it's a very simple answer. Number one, you could have used the cosine, and then you can actually go through the derivation and derive a cosine-based Fourier transform, and that will allow you to represent many real signals. Okay, but if we use the complex exponential, then we can actually represent both real and complex signals very easily using this very fundamental building block. Since you can actually think of a cosine wave as being built up from these complex exponential functions, the complex exponential is actually a more fundamental building block than the cosine. Because I can represent the cosine with a complex exponential, I can basically say, let's just use complex exponential, and then for electrical and electronic engineers, we get this very nice transform which can deal with both complex and real signals. And we're filled with happiness, butterflies, and flowers, and all of those things.